Hello everyone, this is Dr. Zach, and today we are going to begin solving optimization problems. Now, optimizing means you're looking for the largest or the smallest answer within a domain. So let's get started. So as you can see, for your lesson preview, you were asked to find the maximum value of a function. Because your area formula was given to you as a quadratic, you know that the maximum value of your function would occur at the vertex. Now, to find a vertex in Algebra 2, you knew that you would use x equals the opposite of b over 2a and then substitute that value in. So in calculus, you're using the derivative. So a prime of x would be 200 minus your 2x. And you also can take a look and recognize that if you take the derivative and set it equal to 0, that's going to allow you to find where your horizontal tangent lines occur. So this is a different way to find relative mins and maxes, but in this case, we're looking for absolute mins and maxes. So if you take your derivative, set it equal to 0, you come up with x equals 100. You know this is called your critical number. Now, the directions to justify your answer. There are a couple of different ways to justify your answer, but we're going to start with making a table of values. And in the table, you'll place your x and whatever you're trying to maximize. In this case, we're maximizing the area. So the justification is this table of values in which you place your critical numbers and the end points. You have your 0 and your 200. Now, fortunately, the 0 and 200 give you an answer of 0 when you substitute into your area equation. And when you substitute 100 into your area equation, you will get 100 times 100. Now, you expected your answer to be the square. From the extreme value theorem, the maximum value is a at 100, which equals 100 squared. Now, usually you would have some sort of units, but in this problem, we didn't have any. So for question B, once again, you are asked to minimize cost. I'm going to give you some very specific instructions, but for how to solve an optimization problem. So C prime of x is going to be equal to minus 300,000 over your x. And once you're there, you set it equal to 0. Notice you were not told what your values are for your domain, but using the idea that cost is going to be positive, your x values must also be positive. So I hope that you stated your domain went from 0 to infinity so that when you make your table of values, you put in your critical numbers, you put in C of x, whatever that critical number was, and your 0 to infinity. Now, once you substitute your 0 and infinity in, you should have come up with, using the concept of limits, infinity as the answers for C of x. And then, of course, your order size will be the critical number. So optimization problems are used to find the value that is the least or the value that is greatest on a given interval. It's the highest point on the graph or the lowest point, so absolute extrema. Uses for this, they're used in economics, production, environmental sciences, volume, area, energy costs. There are multiple uses for optimization problems, and that's what makes them so important. All right, so for example 1, when you have your problem, the first thing that I would expect you to do, of course, is read it carefully, then draw a picture relative to the problem. We're looking for the largest rectangular area, so draw a rectangle. We want to enclose 75 feet. We enclose this area using 75 feet of fencing. So we're going to put some labels. We'll have X to represent the width, Y to represent the length. As long as your picture matches what you're working on, then that is fine. State what you're trying to min or max. In this case, we're trying to maximize area. Specifically, I want the area of a rectangle. So after that, write down a formula for area of a rectangle. And related to our picture, that would be X times Y. Notice we have 3 variables in this problem, and that's going to be just fine. So next, we would think about your constraint that was given to you. You have 75 feet of fencing. So the perimeter is then going to be 75 feet. And 75 should be your 2x plus 2y. So we now have a constraint equation. We want to write our area equation as a one variable expression. In this problem, I'm going to solve for y. So 75 minus 2x divided by 2 equals your y value. And we substitute. We have x times 75 minus 2x divided by 2. Before you find the derivative, simplify the problem as much as possible because you want your derivatives to be as simple as you can make them. So we will have x squared once we cancel out the 2's. All right, so now once you know what you're trying to maximize, so the domain, that needs to be stated. Let's figure out what it could possibly be. We're using our x values. So the x's, you want to think about the smallest possible x value. In this case, it's going to be 0. The largest possible x value will come from the smallest y value in your constraint equation. And if you were to let y equal 0, then what you come up with for x is 75 over 2. So your domain for this problem will be the smallest x is 0, the largest x is 75 over 2. Make certain that you draw your table of values so that you are demonstrating you understand the extreme value theorem. You're trying to think about the maximum area, put your critical number in. Oh, wait a minute, we didn't find the derivative, so let's find that critical number. A prime of x is going to be equal to 75 over 2 minus 2x, which tells us the critical number is going to be x equals 75 over 4. So place your critical numbers into your table of values. We now have 75 over 4. Put your domain in. We'll have 0 as well as 75 over 2. When you substitute into your area equation, you're going to get 0 and, in 0 and 0. And then for 75 over 4, do your substitution. I use the factored form because the factored form is a little bit easier to deal with. So we have 75 over 4 times 75 over 4. Once again, it turned out to be 75 over 4 squared. Do not depend on that to always occur. Afterwards, from the extreme value theorem, the largest area is 75 over 4 quantity squared, and we know that this is feet squared. Make certain you throw in your unit. For our second example, we are going to maximize the volume of a rectangular solid. So we're going to draw a rectangular solid, but not only is it rectangular, it has a square base. And so the square base gets labeled x, and we need to give the height a different label. So write down what we're trying to maximize. We're going to maximize the volume of this solid. We know that the volume is going to be x squared times y. Now we need to find some sort of relationship between the x, y, and the picture. That's why the picture is so important. You're told that the surface area is equal to 337.5. So finding the surface area gives us 2x squared plus 4xy equals 337.5. From there, you can solve for y. And we'll come up with y equals 337.5 minus your 2x squared, all divided by 4x. Now, why did we do that? We wanted to substitute into the volume equation because we need to make it a one variable expression. So volume equals, distribute x squared. We have x squared times our y, which is 337.5 minus 2x squared over 4x. Once again, do the algebra first so that you have the simplest problem to find the derivative, because that does not need to be a challenge to you. So we'll have 1/2 x to the third. So it comes out to be a cubic polynomial. Nice little problem. Notice again, you were not given the domain. So you have to state your domain in order to use that extreme value theorem. So the smallest value that you could possibly have for this domain is 0. And then we want to go from 0 to, well, let's think about it. Could we go to infinity? No, we're going to use that idea of letting y equal 0 and solving this expression. So we will have 337.5 divided by 2 with the square root. So that is going to be your value. That will be the largest x value. So find your derivative. V prime equals your 337.5 over 4 minus your 3/2 x squared. Once you know that, find those critical numbers. Remember, one of those critical numbers is going to be outside of your domain, so you will not include it, and you end up with 337.5 over 4 times your 2 over 3 with a square root equals your x. So once you know your critical number is 7.5, substitute that in for v of x. You get 604, 3 decimal places, please. 388. There we go, using that AP standard. Now substitute in your endpoints. You have 0, the square root of 337.5 over 2. 0 gives you 0, as does the next one. You put in your 0 as well. So from the extreme value theorem, we know that the maximum area, maximum volume is 604.688 centimeters cubed. However, the directions were asking for the dimensions. So you then need to find when x equals 7.5 centimeters and y equals, you're going to have to find that value. Of course, I want you to follow the process for solving optimization problems. State your objective. That's minimize or maximize. Make certain that you put labels on the picture. Write an objective equation with one variable. You might need a constraint equation for that. Determine your domain. Determine the critical numbers. Prove that the answer is an absolute maximum. Now, to prove it, you're going to use your critical numbers and endpoints in a table, or the second derivative test, which we'll talk about later. All right, so I want you to use these ideas and give question number 1 your best effort. Skip question number 2. There are some mistakes on it. Afterwards, we will continue with question 3. Pause the video now. So let's take a look at what you did for number 1. Did you write the words minimize sum? Did you write an expression for the actual sum that you're minimizing? Next, did you think about some sort of constraint equation? Solve to make a one variable equation. Find your derivative, your critical numbers, and your domain. These were the positive values, so you went from 0 to infinity. Afterwards, you made your table of values, stated your 2 numbers that had answers for x and y, and then your justification would have been the extreme value theorem. Every optimization problem needs a justification. All right, so let's take a look at the second derivative test, which is another way that you can justify your answers. So as you take a look at the second derivative test, you of course find the second derivative. Notice the second derivative in this problem was always positive. So we can say that because the second derivative is greater than 0 on 0 to infinity, s of x is concave up on 0 to infinity. I'm very specific about naming the domain for which this function is concave up. And if it is concave up on that domain, the critical point is an absolute minimum from the second derivative test. So this is a different way to show that you have an absolute min or max for your problem. I would suggest you only use the second derivative test when the second derivative is easy to calculate. All right, so for now, let's take a look at example 3. For example 3, we're going to find the point on the graph of the function y equals square root of x minus 8 closest to the point 2, 0. So when we sketch a graph, we have our square root function. On the graph, we're going to put the point 2, 0. And we'll pick an arbitrary point x, y, so that we can draw the distance between these 2 points, the 2, 0 and x, y. Now, we're looking for closest. So closest means that we are finding a distance, and we're going to have to use the distance formula in order to determine that closest point. So the distance formula is going to be the square root of your x minus 2 quantity squared plus your y minus 0 quantity squared. Now, it's possible that you already see the correct answer for this. So it is possible that you already see the answer to this question, but the work that you're showing is why we solve the problems. So show all the work as you go forward with each problem. You have your distance. We're going to have to find a constraint equation. Notice this is a y value. You know that y is equal to the square root of x minus 8. And when you square that, y squared is x minus 8. Substitute this into your distance formula for the quantity x minus 2 squared plus x minus 8. Next, we are going to take our problem and think about the domain. So the domain for this distance uses your x values. The smallest x value that you could possibly have in this problem is 8. And so we're going to go from 8 to, now think about your biggest x value, that's going to go to infinity. So once you have your domain, you will find the critical numbers within that domain. Now, think about the derivative for a minute. D prime uses a chain rule, not once, but twice. So when you're thinking about your problems, be a little bit creative. Using that chain rule, yes, we can find a derivative, no problem there. But if we're going to minimize distance, could we also minimize the distance squared? So think about that for a minute. If we were to take the distance and square it, that value is also going to be the minimum of your distance. And isn't the derivative of distance squared a whole lot easier than the derivative of the square root function? So now, if you think about it that way, there we go, nice little derivative. Find your critical number. We get 2x minus 4 plus 1 equals 0, or x equals 3 over 2 as the critical number. When you go to make your table of values, you can still put in x and d because, once again, you are minimizing distance. The critical numbers, 3/2. Your endpoints are 8 and infinity. All right, so when we substitute 8 into our distance formula, we get the square root of 36, and that becomes 6. When you substitute infinity, you get infinity. When you substitute 3/2 into your function, maybe you started to recognize 3/2 is not even in the domain. This does not have a critical number at all. So the end point, 8, is where you're going to have your minimum distance. But you had to show it. So from the extreme value theorem, we know that the minimum, the closest point, that's good, is 8, now be careful, it's not 8,6, it's 8, 0. Substitute it back into the y value. So use your endpoints. You have to check endpoints as you do each of these problems. All right, give numbers 3 and 4 a try. Follow all the steps and you're going to be set. So the answers to your questions have been stated. Make certain that you show all of the work to justify these answers. So your lesson follow-up, you have 7 questions that I want you to work on. Give these a good try. Make certain you show all of the steps that we discussed within this lesson. Have a great day.